Yeah, it works.
Okay, thanks. Okay, sorry.
Okay, so good morning everyone, and we start after some technical issues. My topic is very clear, so I'm not going to read it again, I guess, but only thing that I have highlighted is Rheo and optics in two different colors, because it's combination of two different fields. One is rheology, the other is optics. And I'm not sure if how much knowledge do you have about rheology, but here it says it's the science of deformation and flow. I will explain it in more detail. Optics is optics, like it's simple, but I will explain in my research context where I'm going to use the optics. The overall frame of my presentation is like I'm going to give you a brief introduction of rheology, then I'm going to explain you about optics, what I'm going to use, and after that, if I find time and if you are still interested, I will just give you a brief overview of my research. Coming towards rheology. Rheology is the science of deformation and flow. So here on the graph, if you see, you have different variety of materials. On the very left, you have a droplet, that's liquid, then an oil, a shampoo, then you have a cream and a jelly. And on the very right hand side, you see that you have a box, that is a green box, it represents a metal. So from left to right, you see the change of material, state of material is changing. Like a shampoo is liquid, but it's not really like liquid, it's liquid like, but how much liquid it is, how much solid it is, how do we know? Or on the other side we have a jelly, it's like solid, but it's not really a solid. How much solid it is and how much solid it should be if you want to enjoy jelly. These type of things actually we study in rheology. One more example from your day-to-day life is mayonnaise. If you have it in breakfast and you just took a spoon out of it, and if you leave the bowl like this, it will stay like that for a long time. But I let you imagine that if that box was of honey, if you don't like mayonnaise and you have honey in breakfast, if you take spoon out of it, what will happen to it? The surface will go back. It will not be like this. So what is the difference between a mayonnaise and honey? How do they change and why they have a different behavior? One more example is the toothpaste. You have brushed in the morning, I believe. So we have different requirements. What we want, like we want when we are pushing the paste out of the tube, we really want it to come and flow, but on the brush we want it to stay. But when we are brushing our teeth, we want it to flow nicely again. So these are complex requirements. To characterize this, to quantify this, and to make it work like this, this is what actually rheology does. So I will stop the introduction or the idea of the rheology here, and I will go to the next topic of optics. At this point, if I am able to convince you about rheology, okay. If not, you can come back and ask me questions after the presentation. Coming towards the optical path. Optics is simple, it's the use of the principles of the optics. You're using some sort of light, it can be laser, it can be optical light. Here is one example. I think you have used sunglasses at one point in your life if you went to a beach. And if you have two sunglasses and if you just make them cross, you see no light coming out of it, right? Because they are acting as a polarizers. Now in this case, we have a light source, we have two polarizers crossed, and the detector is light, is your eye actually that is detecting the light. The polythene bag is a normal bag and light passes through it. Now what happens? If you just stretch it, if you stretch, some degree of light will come out from the same setting of the polarizers and the light. What happened? The chains got aligned, and because of that the polarization state of light got changed. If you can measure the quantity, if you replace your eye and you have a detector that can quantify, okay, zero light and some light is coming, you can relate this quantity of light to how much your polymer chains are stretched. So this is the idea of the optical plane. Now I am working on lubricant as the chair has introduced in the start. Lubricants, what is the basic formula? Basic formula, as you have seen also in my very first slide, you have the base oil, you add some additives and you get the final product. Over the left, you see that 53% of the lubricants are used in the automotive industry. So that's my focus point. And it adds a lot of cost actually. What I'm going to do with this, I give you an example that is related to you. Extreme weather conditions and you have to drive. If you have seen this meme, it's like no offense to anyone, but in the winter, maybe your wife calls you and she gives you this message that okay, the car is not starting and some person is sitting over there. It's not because of that, if some person is sitting over there, but you have feel this like in the winter, you need some time to start your car, right? It takes some time to heat up. What happens? You have this oil, just imagine. If you cool it down, what will happen? It's a common thing, it will become thick. It will not flow as it should flow. So you have to heat it. And if it is really become very highly heated, then what happens? The surfaces will touch more often and life of your engine will decrease. So we really want to avoid these two weather extreme conditions. To do that, we have these polymer additives, not the person. Polymer additives. What the polymer additives do, they try to make a constant viscosity of our oils. So if you go to the low temperature, or if you go to the high temperature, the viscosity doesn't change. So your oil doesn't become very thick or it doesn't become very thin. And that's the idea of having these lubricants. What I'm doing with my PhD, I want to study the rheological behavior of these lubricants, and I want to design a novel shear cell that can actually provide the high shear rates. High shear rates I will explain in the next slide also. And with that I also want to study it using optics, because at high shear rates phenomena are taking very fast, so I want to study. What is shear rate? If you are not clear, just example over there, it's you are shearing your material. So you have a speed with which you are shearing and you have a gap, measuring gap in between. So if you want to increase the shear rate, either you can, let's say, decrease this gap or you can increase the velocity. If you increase the velocity, the flow becomes very much abrupt. So the idea is that we go for the smaller gaps that will give us increased shear rate. Why we want increased shear rate? Because this is an example of how the engine works. These pistons, they move really fast. So if you see these colorful materials, the oil, let's say, it's moving between the piston and the wall. So the gap is very low and the piston is moving very high. So if I just go back to my previous slide, very high velocity, very small gap, it's going to give me a very high shear rate. In commercial rheometers, we don't have such capability possible that we can really test using these high shear rates. Because of that, I have to design a shear cell that can go for higher gaps. And then also I have to set up an optical train with which I can study the optical parameters simultaneously. So I'm getting some value from my mechanical device, my novel shear cell. I'm getting some parameters from my optical parameter, and then there is a stress optical coefficient. It relates both. So I can also compare my results using two different techniques and simultaneously see how much I am out of the range. Then this is the setup that I have. On the top I have the optical train, then everything in the blue is the optical train component, and here I have my sample. Here I have my rheological setup with which I measure my rheology. How it looks like, actually it looks like this. Again, the laser comes from here, it hits the prism and it flips down, and there I have the other components that I have shown before, like a lock-in amplifier and a computer. And over the time, it was like in the start, then it got modified. So you see, I have a glass plate here, and this is a transparent rheological device which makes a rheology. So laser passes through it and goes down to my detector. And over the time, there were some modifications in it and some mobility. So if you don't remember anything, and if you don't remember rheology or all, I like to leave only 3 imprints with this talk. First, rheology is a very powerful characterization tool, and it's a day-to-day tool in your shampoos and day-to-day life. If we combine rheology with optics, it gives us several other additional possibilities to characterize. And last, not the least, with my setup, we will be able to nicely understand these polymer additives behavior, and with that we can reduce the cost and we can make our cars more efficient. With that, I'd like to thank you all for your attention, and I'm open to welcome questions from any direction. Thank you.
Thank you, Afsar, for this talk. let's open the floor for questions. Who would like to start?
Yeah. So I was wondering, you are studying the behavior of the oil, but how are you going to use it in practice to adapt it and to change things?
Yeah, it depends on what do you mean by how I'm going to adopt it, like how I'm going to really use it in the engine. That's not the idea.
Okay.
The idea is to produce the same conditions as we have in the engines in my setup. So as I have mentioned, like in my slide, that one of the goals of this PhD is to develop a novel shear cell. That shear cell is going to produce the same conditions as we have in engine in the lab. So we don't need to really apply it there, but we need to test it here and then we can apply it. Yeah.
Okay. So zinc oxides, which are commonly used lubricants in engine oils, are, in my opinion, superior because they are, or forget my opinion, they are superior because next to reducing shear, they also prevent oxidative corrosion. Correct me if I'm wrong.
I agree to some extent, but in my experience, it's not the case because zinc is a metal, and again, it's going to release in the environment, and you have a lot of environmental concerns. We have hot topics like environmental issue and sustainability. So if you remember the first title slide, it says that I'm working with the polymer additives. They are environment friendly and they are organic. So that's why this is the area I have chosen to work it and not with the zinc, because in next few years with the environmental issues and sustainability, it's going to be a problem and we are not going to use it anymore. Yeah.
I think we'll stop with the questions right there, so you can take your questions during the break to the speaker.
Yeah.
Thank you everyone for your questions, and let's thank the speaker again for his talk.